center networks. This work was jointly done at Peking University and Huawei Cloud. My professor, Qun Huang, is the corresponding author. So, data center network monitoring is indispensable to providing reliable cloud services. Given modern scales of the data center infrastructure, failures are the norm rather than exception. Here are some major failures in a region in Huawei Cloud in the past 18 months. They dragged down the quality of service for tens of thousands of users. Moreover, they took 10 hours on average to repair and had diverse root causes like port flapping, state mismatch, chip errors, and card errors. A natural question to ask here is, why this failure took so long to repair? Now, let's dive into one such case where one of the 8 aggregated ports flapped about every 30 seconds. In this scenario, we had 8 member ports on each of the 2 peer switches. They were connected by 8 physical links. We configured on both of these switches to bundle these links into a link aggregation group, or LAG in short, so that they collectively functioned as a layer 3 interface. The forwarding rule in the LAG is basically 2 steps. First, the IP routing table decides a packet should go through this LAG interface. Then, the proprietary layer 2 hash select one porting at random in the LAG to forward the packet. We had 12 probe tasks through this LAG interface, where each task is something that just injected synthetic traffic between host and trace metrics like RTTs and loss rates. Each task could exercise one of the many types of pings and so on. However, none of them went through the flap port. A quick calculation shows that this could happen with more than 20% probability, which was not rare. So, effectively, we covered this layer 3 interface, but not all of its member layer 2 ports. Meanwhile, all of our deployed tools didn't raise any alarms, including NetFlow, SNMP, BGP monitoring protocol, and ERSpan. We finally resolved this issue by isolating and restarting the buggy port. So, after studying all these failures, we find the common culprit in the insufficient layer 2 coverage, since all of them occurred on uncovered layer 2 ports. So, with respect to coverage granularity, we favor layer 2 over 3. Layer 3 coverage means every layer 3 interface has some task going through it. It is not good enough since an interface can be a bundle of layer 2 ports where each port has its own working status. Even if a layer 3 interface looks good to quite a lot of probe tasks, some of its member ports can still be degraded. And here is a simple scenario where we configured LAG in Huawei Cloud. Yeah, so it's called ETH trunk in Huawei Cloud. And next, as per sufficient coverage, we find 99% is a satisfying threshold, and a strict requirement of 100% coverage is totally unnecessary. 100% means all ports are covered. It has 2 drawbacks. First, the resource overhead is overly high in complex data centers, as we will shortly see. Second, the benefit gain from 99 to 100% is only marginal. And in fact, a coverage briefly higher than 99% already significantly improved the accuracy of failure detection. So to illustrate, we inject simulated random drops into a closed network containing 10,000 switches. We fix the detection algorithm and vary the set of probe tasks so that they can achieve different coverage levels. When the coverage rises from 97 to 99%, the false positive ratio reduces from 4% to nearly 0, and the false negative ratio reduces from 10 to only 3%. Similar trends are also observed in detection of other types of failures like congestion-related packet drops. So it's time to introduce the formal definition of layer 2 coverage. We'll express it in 2 variables, alpha and p. Alpha indicates the intended number of tasks through each port, whose typical value is between 1 and 5. And p is the portion of layer 2 ports that have at least alpha tasks through it. And sufficient coverage simply means p is no less than 99% for an operator-specified alpha. We let alpha and p be the input of our system, and our task is to generate tasks for filling alpha p coverage. A good question here is, why don't we maximize p? And I think a brief answer is that theoretically, P can be infinitely close to 1 if you add tons of tasks, but this leads to high overhead and marginal gain. We can identify 2 challenges concerning sufficient layer 2 coverage. The first one is complexity. Many deployed techniques can blur the view of layer 2 ports and drive the path control on layer 2 infeasible. For example, in Huawei Cloud data centers, there are 4 such techniques that are deeply connected to each other, namely link aggregation, switch stacking, virtual routing and forwarding, and equal-cost multipath routing. What's worse, switch vendors mostly do not disclose detailed layer 2 metrics due to reasons like proprietary and security concerns, maintenance burden, and potential speed down. So most available metrics are up to layer 3 level. The second challenge is scalability. As probing is resource constrained, it is desirable to keep the probing plan time within a few minutes in order to respond to network changes promptly. Moreover, we must ensure each server exercises no more than a few hundreds of tasks due to the tight CPU and NIC budget available to a server. Sadly, our old PMesh-like monitoring method can't address this challenge. It achieves an estimated coverage of around 80%, far from being sufficient. Although it has low planning time due to its full mesh probing method, it produces a prohibitively high probe volume. For example, if you want to improve its coverage by slightly increasing task numbers, then about maybe 10% of servers are likely to be overloaded. Unfortunately, existing solutions fall short of addressing these challenges. We classify them into 3 categories. The first category treats switches as black boxes. This includes methods from network tomography and full mesh probing. Traditionally, they focus on layer 3 coverage, and lowering to layer 2 is non-trivial. They also have scalability issues since the optimal planning is NP hard. In fact, they usually sacrifice either time or volume to satisfy the other. The second category treats switches as white boxes. This includes methods like packet sampling, in-network telemetry, and measurement. Promising as they are, their power is limited by the built-in capabilities on hardware. They can be intrusive and even incompatible with existing devices. Nonetheless, we deem them as good complements, and they can be used in combination with our system for better performance. The last category is network verification. And we have already used config verification tools like the Batfish here in Huawei Cloud. Note that they focus on verifying static properties by analyzing a snapshot of the network. Instead, here we aim at continuous monitoring. To this end, our contribution is a new monitoring system, RDProbe. It's fully aware of complexity in production environment and is guaranteed to achieve sufficient coverage. It is also designed to achieve high scalability and fault tolerance. Finally, it has large-scale deployment in 3 production regions. Now we take a look at RDProbe's architecture. It has 5 epochs in it has 5 steps in an epoch, which usually lasts for like maybe 3 minutes. It begins with topology construction, which aims to tackle the complexity challenge. To do so, it reveals all layer 2 ports and their mutual reachability by transforming a layer 3 topology. The resulted topo, which we call the de facto topology, can be different from that on either layer 2 or 3. Next, we come to the kernel of RDProbe, namely 2-phase generation. It ensures sufficient coverage while addressing the scalability challenge in 2 phases. Phase 1 is randomized generation. Its high-level idea is that we can randomly select tasks with arbitrary sources and destinations, so the most ports are evenly covered and sufficiently covered. Then phase 2, also known as deterministic generation, will complement phase 1 to reach the prescribed coverage requirement. It produces additional tasks through the yet undercovered ports. To summarize, by combining randomized and deterministic method, we can realize better planning time and probe volume simultaneously. 2 additional steps come between phase 1 and 2 to provide feedback. The first is packet mirroring, which mirrors probe packet to the control plane of a region. After that, it goes the coverage computation, which listens for mirror packets and computes layer 3 coverage counters. And these counters will guide phase 2 in locating undercover ports. Having seen all the overall architecture, let's delve into a bit details. Recall that topology construction incrementally modify a layer 3 topo into a de facto one. The key idea is that we can parse related switch configurations into equivalent graph operations. And here is a minimal example. Assume we have the topology on the left. And the configuration for this lag will look like this piece of text. And we know from it that 2 GB Ethernet ports are member ports. So in layer 3 topo, we have only one logical link representing this connection, and we issue a split edge operation, and this edge will become 2 physical links in the de facto topology. Note that one configuration can translate to multiple operations, and we encourage you to read our paper for more complex examples. Also, concrete details of topology construction are up to the data centers themselves. We show how it's designed in Huawei Cloud. Now we're ready for phase 1, where we have coverage requirements and de facto topology at hand. To produce phase 1 task, we randomly select tasks for an even coverage. For now, we assume we need T task and have A healthy centers. Then each server will randomly select T over A destination servers for load balance. So the crux here is, how can we know T? That is, how many tasks we need in phase 1. And here's the insight. We can model phase 1 using the coupon collector theory. It allows us to relate T and the achieved P for any given alpha. Assume there are S switches in the network and the largest switch has M ports. We have 3 key results. First, we can efficiently determine the value of T. That is, determine how many tasks we need in phase 1. Next, our T will not be much larger than the optimal volume, which is NP hard to find, of course. Finally, a vast majority of ports are sufficiently covered in phase 1. So these key results together guarantee the performance of phase 1. And now we can proceed to discuss phase 2, where we've got our layer 3 coverage counters. The idea here is to first locate undercover interfaces so far, and then find additional tasks through them. So how to locate undercover interfaces? Well, again, we use coupon collector theory to find how many tasks are needed per layer 3 interface. Those whose coverage counters are below the required value are our targets. Then, how to find additional tasks through it? It turns out that we use BFS to find the nearest neighbors. Moreover, to ensure that the newly added task goes through it, we exercise IP-EMP ping for path control. Finally, we don't use phase 2 from scratch due to 2 reasons. One is that it is only effective after most ports are covered. And second, it cannot exercise protocols beyond IP-EMP ping. So now we show the deployment result. All the 3 deployed regions have around 1,000 switches and tens of thousands of links. Not only does RDProbe guarantees sufficient coverage, it also improves coverage with even fewer tasks. We also case study how RDProbe helps detect new failures and tolerate numerous production faults in paper. So we encourage you to read it. And we further conduct large-scale simulation on NS3 using 2 popular topologies. Their scales in an order higher than the deployed regions. Besides sufficient coverage, we find issues good scalability results. For example, the volume is about switch number to the power of 1.53. The optimal power we can expect here is 1.5, so it is only 300 larger. Besides, the planning time is strictly within 1 minute, even at the larger scales. So, compare with previous industrial solutions, including ping mesh, net bouncer, and detector, we find that RDProbe is the only one achieving sufficient coverage and scalability at the same time. And here the results are also obtained in our large-scale simulator, which is customized from NS3. Yeah. And to conclude, we first discovered the fact that sufficient layer 2 coverage matters and suffices. And then we find the challenges of complexity and scalability make it hard to achieve. We tackle complexity by topology construction and scalability by two-phase generation. And last but not least, RT-Probe is designed to be an industry-grade solution and demonstrate SOTA performance. Yeah, and that's all for my presentation. Thank you for listening, and I'd love to take any questions.
Okay, if you have Hello. Yeah, if you have questions, please line up at these two mics. And before you ask a question, please say your name and your institute. Okay, as we are waiting for questions from the audiences, let me ask a question. So it seems the hyperparameter alpha is very important for the performance. So how is it tuned in practice?
Well, actually, alpha is where the operator's experience come in. And in RT-Probe, we let the, In RT-Probe, we let the data center's operator specify alpha, which is typically between 1 and 5. And currently in Huawei Cloud, we find an alpha equals 1 is already able to help us detect many more failures. And in some maybe regions where you require a more stricter reliable services, maybe you can specify a higher alpha. Yeah, but
do you need a different alpha in different data centers?
Oh yeah, for example, here in these 3 centers, we tested alpha with whose value equals 3, and for other maybe smaller data centers, we find also a smaller alpha suffices. Yeah.
Okay, and could you share some insights in practice? How do you fix the problem after you root cause it?
Well, actually, it's quite a tedious job because many failures requires you to manually reboot or isolating the buggy components. Yeah, so I'm afraid there's no universal solution to troubleshoot or debug. Yeah.
Okay, I see. So, wow, a very naive question. So it seems in data centers, there are a lot of, there's some spare capacity and they use ECMP. So why is it unreasonable to just say join the traffic, migrate the traffic to some spare, like other switches, because they are multipath, and do the troubleshooting offline?
Oh, yeah. Most typical troubleshooting are done maybe offline after you isolating the faulty component, and meanwhile, the affected traffic rerouted to another normal path. Yeah, so that's a typical case. But if in very rare scenario, we have a failure that could affect a whole switch or a whole like TOR or maybe core. That's an issue that we rarely encounter, and if that does happen, we kind of like, oh no, the service current is temporarily down, and yeah.
Okay, thank you. Let's thank our speaker again.